welcome all to the lecture series of the subject Embedded System, which is an open elective with the subject code KOE 062, and it is being taught in all the branches of engineering. Today, myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. I am going to deliver the lecture on the topic inter-process communication, which is an important topic of real-time operating system. What is inter-process communication, that is IPC? Let us understand this first. We can define a process by the two types, that is independent process and cooperating process. An independent process is not affected by the execution of other processes, while a cooperating process can be affected by the execution of other processes. Though one can think that those processes which are running independently will execute very efficiently, but in reality this is not the case. Many a times the processes need to share the information, need to share the messages, or we can say the resources among each other in order to increase the computational speed, convenience and modularity. So, inter-process communication is a mechanism to facilitate this, and it allows the processes to communicate with each other and synchronize their actions. Let us understand the inter-process communication mechanism in detail. The communication between these processes can be seen as a method of cooperation between them. The processes can communicate with each other through two mechanisms, that is the shared memory and the message passing. These two figures show these two processes, that is the shared memory and message passing. As we can see in the shared memory, this is process A, this is process B, this is kernel. As we all know that kernel is the heart of any RTOS. So, what is happening that this is the shared memory. So, this is a resource that is being shared between the two processes in the inter-process communication. So, whatever suppose the process A has saved some messages, some information in the shared memory, and now process B wants to use that same information which is being shared by process A. So, it can easily access the shared memory and can use the information. So, this is how the shared resources are being used between the two processes in this mechanism of shared memory. What is happening in message passing? Suppose again the process takes place through the kernel. The process A gives some message to the kernel and the same message is passed to another process, that is process B. So, this is the mechanism of message passing. So, in the shared memory method, the communication between processes using shared memory requires processes to share some variables, and it completely depends on how the programmer will implement it. One way of communication using shared memory can be imagined like this. Let us understand this using an example. Suppose process 1 and process 2 are executing simultaneously and they share some resource or use same information from another process. The process 1 now generates information about certain computations or resources being used and keeps it as a record in the shared memory. So, same is the scene that process A has kept some computations or the resources being used and it has shared recorded, keep it as a record in the shared memory. So, when the process 2 needs to use the shared information, it will check in the record stored in the shared memory and take note of the information generated by process 1 and act accordingly. So, this is how the same information is being shared between the two processes, that is process 1 and process 2. In the message passing, if the two processes P1 and P2 want to communicate with each other, how this is done? That establish a communication link. If the link is already existing, no need to establish it again. Second step is start exchanging messages using basic primitives. So, as now we will try to understand the term basic primitives. So, there should be at least the two primitives, that is the send and receive. So, in the send, the message as well as the destination can be specified, or simply a message can be specified, and in the receive primitive, again the message and the host can be specified, or simply a message can be specified. A standard message can have the two parts, that is the header and the body. What is the header? Header part is very important. It is used for storing message type, destination ID, source ID, message length and control information. The control information, what is this? It contains the information like what to do if runs out of the buffer space, sequence number, priority. Generally the message is sent using the FIFO style. So, what is happening in the control information? That everything related to the control of the sending and the reception of the messages, this is being controlled using the control information. So, FIFO style is first in first out, simply like a queue. So, we can understand this using this figure. This is the sending process, message passing module is this is the receiving process, message passing module is this is being received here, and this is the process ID and along with the message. So, this is the whole header and the body part. Now, when we are talking about the inter-process communication, there are various ways of this mechanism to take place. Pipes is one of them, and what is this? A pipe is a technique used for inter-process communication. It is a mechanism in which the output of one process is directed into the input of another process, just like a simple pipe. This is the analogy. Thus, it provides one way flow of data between the two related processes. So, like in the pipe, that there is an inlet and there is an outlet, likewise the message entering the pipe will be flush out from another end. Although the pipe can be accessed like an ordinary file, the system actually manages it as a FIFO queue, that is a first in first out. So, something that will enter the pipe will be flush out, then likewise in this using this mechanism, some messages or some information that is entering the pipe will be flush out. A pipe file is created using the pipe system call. A pipe has an input end and an output end. One can write into a pipe from input end and read from the output end. A pipe descriptor has an array that stores two pointers, one pointer is for its input end and the other pointer is for its output end. So, this is how the mechanism is taking place in the pipes. Now, suppose there are two processes, process A and process B. Let us understand this with an example, and they need to communicate. In such a case, it is important that the process which writes closes its read end of the pipe and the process which reads closes its write end. So, this is the necessity. Essentially, for a communication from the process A to process B, the following should happen. What should happen? A process A should keep its write end open and close the read end of the pipe, and process B, since it is reading, so it has to keep the read end open and close the write end. So, when the pipe is created, it is given a fixed size in bytes. So, according to the message, it is giving the fixed size in bytes. So, what is happening when a process attempts to write into the pipe? The write request is immediately executed if the pipe is not full, but if the pipe is full, then the process is blocked until the state of the pipe changes. So, it has to wait. Similarly, in the reading process during the reading process, the process is blocked if it attempts to read more bytes that are currently in the pipe. So, otherwise the reading process is executed, only one process can access a pipe at a time. So, this is the limitation of using a pipe. So, this is what is happening. So, this is the pipe, there is already a message in the pipe, the task is of the writing is being introduced from this end and the task of reading is done from this end. So, this is how the task is of reading is done. This is another part, that is an interrupt service routine. Through the interrupt service routine also we can access the pipes. So, what are the limitations of using the pipe? As a channel of communication, a pipe operates in one direction only. pipes cannot support broadcast, that is sending messages to multiple processes. This is not possible in the, while using pipes, because it is having only one end of reading and one end of writing. So, how the broadcast is possible? So, that is why it is not possible. The read end of a pipe reads any way, that is, it does not matter which process is connected to the right end of the pipe. Therefore, this is very insecure mode of communication, because whatever is available at the reading end, it will read. So, this is somewhat very insecure communication. Some plumbing, that is, plumbing is the closing and the opening of the ends. So, such mechanism or should be implemented through the algorithms which are required to create a properly directed pipe. So, this is another limitation, another constraint. So, due to these constraints, while using the pipes, pipes are not very much popular for the inter-process communication. Let us see another type of mechanism in the inter-process communication, that is the mailboxes. Mailboxes provide a means of passing messages between the tasks for data exchange or task synchronization. For example, assume that a data gathering task that produces data needs to convey the data to a calculation task. So, that consumes the data. This data gathering task can convey the data by placing it in the mailbox, and using the send command, the calculation task can receive the data. Okay. So, when the calculation task, so data gathering task can convey the data by placing it in the mailbox, and on the other end the calculation task will receive that particular data. If the calculation task consumes data faster than the gatherer produces it, the task needs to be synchronized. So, maybe the speeds of the two ends can be different. So, maybe the data gatherer is slower, or data gatherer is faster than the other, that is the data calculation task. So, using mailboxes achieves synchronization by forcing the calculation task to wait for the new data before it operates. So, in this way the mailboxes are used to achieve the synchronization when the speeds of both the ends are different. The data producer puts the data in the mailbox and sends it. The data consumer task calls receive to check whether there is a new data in the mailbox. If not, receive calls pause to allow other tasks to execute while the consuming task is waiting for the new data. So, this is how the synchronization is taking place between the data gatherer and data calculator using mailboxes. So, this was the importance of using mailboxes for synchronization. Now, let us come to another mechanism of using the mutex and semaphores for this synchronization mechanism of inter-process communication. So, designing an embedded system that employs a real time operating system with multitasking behavior. So, this is an important characteristic of using the real time operating system, that we have to deal with the multitasks. So, it means that there will be resources that must be shared between the tasks. So, how this sharing of resources is facilitated, how the sharing of resources is synchronized and is done without any confusion. So, how this is done, let us understand. These shared resources, the shared resources can be peripheral modules, data structures, communication interfaces. So, by their nature does not support multiple concurrent accesses. Okay. So, but now how they are accessed by multiple tasks or multiple processes, accessing them without any rules in place may cause undesired behavior of our program. So, therefore, mutex and semaphores, these two mechanisms are required in different scenarios to synchronize the sharing of these resources between the different processes. So, how the mutex works? A mutex is the mutual exclusion. So, mutex is basically the short form of the term mutual exclusion, and it is a locking mechanism. It is used for protecting critical sections of the code. What is critical section? It is defined as the piece of code that accesses shared resources of the embedded system. So, that is the critical section. So, mutex is used in protecting these such sections. A situation can arise where the critical sections from different real time operating system tasks try to access the same resource, or we can say a shared resource at the same time, enabled by preemptive scheduling algorithms. So, during the preemptive scheduling algorithms, this situation can arise that the different tasks are accessing the shared resource at the same time. So, what will be the solution to this situation? This is a mutex. It can be used to protect critical sections while maintaining the multitasking behavior. So, as embedded system designers, it is our job to identify the critical sections first, and then we can use mutex. How the mutex is used? It behaves like a token, that is a key, and it restricts access to the resource. If a task wants to access the protected resource, it must first acquire the token. So, if it has already taken the token, the task could wait for it to become available. So, if the token is already acquired by another task, then the task which is waiting for which desires to access the shared resource, it has to wait for the token. So, once the token is available, the token is owned by the task and is released once the task is finished using the protected resource. So, this is how using the mutex like a token helps in achieving the task of synchronization between the shared resources. So, mutexes are available in every RTOS, can be accessed through APIs. These are common operations that the RTOS task can perform the mutex. So, that is we can create or delete a mutex. We can have the ownership of the mutex, that is acquire a lock on the shared resource, and we can also release the ownership, that is release a lock on the shared resource. So, this is what actions can be taken while using the mutex. So, this situation is quoted using this figure. So, this is the initialization process, mutex is unlocked, again now the ownership is acquired by some task and it is again locked. So, when the task gets completed, it will again release the token and it gets unlocked again. So, this is how the state of the token gets changed, or we can say the state of the mutex gets changed while using. Now, another important term related to the mutex is the priority inversion. It is a situation in which a lower priority task prevents a higher priority task from running. Because this is opposite to the scenario in this is contrary to the normal scenario, that a task with a lower priority is preventing the task with a higher priority from being executed. The occurrence of this priority inversion is undesirable and cause serious problems in the real time applications. So, this has to be handled wisely. Let us understand this situation using an example. A higher priority task is trying to obtain a mutex that is owned by a lower priority task. The higher priority task is blocked waiting for the mutex to be freed. Meanwhile, other tasks that have an intermediate priority level and do not need to use the shared resource locked by the mutex, such tasks can interrupt, or we can say such tasks can preempt the low priority task that is holding it. So, this may significantly delay the execution of the higher priority task. So, this is known as the problem arised due to the priority inversion. So, what is the solution to this problem? The built-in protection is activated when a higher priority task is trying to obtain the mutex that is owned by the lower priority task. So, there are two ways to handle this situation, that is the priority inheritance mechanism and the priority ceiling mechanism. In the priority inheritance mechanism, the priority level of a task owning a mutex is increased only when another higher priority task tries to obtain the same mutex. The new priority level is set higher than that of the requesting task. So, this is how the actual priority of the task is entertained. Now, priority ceiling mechanism, each resource has a priority ceiling value assigned. So, the priority level of a task that acquires the mutex protecting the resource is increased accordingly, so that it can match the ceiling value of the task and it can acquire it. So, this is how the problem of priority inversion is solved. Let us discuss at last about the semaphore. It is again like the mutex, but it is not used as a token, rather it is a signaling mechanism. It is available in real time operating systems with some subtle differences in its implementation. These are used for synchronization between the tasks just like the mutex, and it manages the allocation and access to the shared resources. Semaphores are usually accessed through the API again, just like mutex. Here are main operations that a task can perform with the semaphore, that is creating it, next acquire a semaphore or release a semaphore, and moreover there is one more task, that is semaphore can also be deleted. What are the types of semaphores? There are mainly two types of semaphores, that is the counting semaphores and the binary semaphores. Counting semaphore has two main applications, that is the managing resources and counting events. So, the count value of the semaphore indicates the number of available resources. A separate semaphore can be used for each different type of shared resource. So, this is used to indicate the number of available resource. And what about the counting events? An occurrence of an event will increase the count value of the semaphore. In this way, we can count the number of events taking place. So, this is how the semaphores are used for two tasks, that is managing the resources and managing the counting, that is the counting of the events. So, this figure explains the use of semaphores. Suppose this is the initialization process, initial count is greater than 0, that means the semaphore is now available. So, after the acquire, the count decreases. Now, if the count reaches 0, it means the semaphore is now unavailable. Now, again if it is released from the task, then the count is 1. So, it means when it is released, then the count increases subsequently. So, this is how the value of the semaphore increases or decreases according to its acquire or it is released. So, and what about the binary semaphore? It is a simple signaling mechanism, it can take only two values, that is 0 or 1, that is why it is known as the binary semaphore. It is most commonly used as a flag for synchronization between tasks or interrupts and tasks. So, this is how it can be understood using this figure. Initial value is 1, it is available. If it is acquired, the value becomes 0. So, we can understand that this is unavailable. Now, again the initial value is equal to 0, and when it is released by the particular task which is using the semaphore, then again its value becomes 1. So, we can understand that it is available now. So, this is the state diagram of the binary semaphore. So, using an example, let us understand the situation. We have an interrupt service routine that stores every new ADC conversion result, and we have a task that takes this result and displays it on the LCD. So, now how the semaphore can be used in handling this situation. A binary semaphore with an initial value of 0 is created. When a new ADC conversion result is available, the ISR will release or give the binary semaphore, that is the value of the semaphore becomes 1. The task will check the value of the semaphore. So, if the new conversion result is not available, the semaphore will be 0 again. So, if the value is 1, this means a new result is available, and if it is 0, it means the result is not available. And when the value is 1, and so it means that the result is available, so it can be displayed on the LCD. The task acquires, that is, takes the semaphore, setting it to 0, and in this example the semaphore is used as a flag with the two values, that is 0 and 1. So, here we are using which type of semaphore? Binary semaphore. So, in this way there are different types of mechanisms which can be used to facilitate the inter-process communication, and these are the mutexes, semaphores, pipes, mailboxes. These are all the mechanisms to facilitate the inter-process communication, and among these we can see that pipes are not so popular because of the various constraints with the pipes, and the most popular are the semaphores, and next the mutexes, then mailboxes, and then pipes. So, this is how the interprocess communication takes place between the various processes. So, that was all from my side, and in the next lecture we will talk about the other part of the real time operating system. Till then, that is over for today. Thank you.